So here we have a question involving vectors and a little bit of geometry. So we're asked to apply the dot product for vectors to prove that the diagonals of a square intersect at right angles. Okay? So you kind of led a little bit on this one. We want to apply the dot product. Okay, so we've got a square. So all these sides are equal in length. And if we're going to use the dot product, essentially two vectors are normal or orthogonal or perpendicular, however you want to talk about it, if their dot product is 0. Right? So the angle between them will be 90 degrees. Okay, so if I... Let's just label our corners first. Say A, B, C and D. All right, and what I'd like to do, let me draw in the diagonals. Let's see if I can do that. Kind of want to show that these things cut at right angles, really. Okay. Oops. Okay. All right. So we're asked to essentially use dot product, so they want us to use vectors for this one. So how do we do it? Well, first of all, let's think about what we want to achieve. We want to show that, say, AC is perpendicular to, say, I don't know, DB. So with that sort of notation, this is what I mean by the perpendicular or normal or orthogonal. And to do that, what we're going to do is show that the dot products are 0. Okay, now with a lot of these questions involving, parallelograms or rectangles or something like this, you want to use the triangle law for addition. Okay, so let's see if we can write the vector AC and DB in terms of vectors associated with the sides of our square. Okay, and because it's a square, all the lengths of the side vectors will be equal. Okay, so AC is going to be AB plus BC. You don't have to make these choices, but they're just the ones I've made. And DB is, I'm going to say it's going to be DC plus CB. Just again by the triangle rule. Oh. Okay, now if you make a mistake, you can always just check the algebra by covering up the middle letter. Okay? All right. So, forget about that. All right, so let's take the dot product of these two things. We can distribute it because you know the distributive law for dot products. AC dotted with DB is going to be this. And I'm going to expand this in the usual fashion just by keeping the dot product between all the terms. Okay, so AB dotted with DC plus AB dotted with CB plus BC dotted with DC plus BC dotted with CB. BC dotted with CB. Okay, so it looks like we've actually made the problem more complicated. But now we can use some of the properties of the square to simplify this mess. Okay, so let's look at this one first. I'll save this for later. Let's look at this one. AB dotted with CB. So AB dotted with CB. What is the dot product of those two things? 0. Why? Because you've got a square and we know that they'll be perpendicular to each other. Okay, so that's going to be 0. BC dotted with DC. Well, we'll dot product of those two things. They're at right angles, right? So they're 0. Yeah? Now the last two terms, AB dotted with DC. So AB dotted with DC. Now vector AB has the same length in the direction as vector DC. All right? So I can actually write it like this. Because vector DC has the same direction as AB, and it's a square, so it has the same length. What about BC with CB? BC dotted with CB. Right, so BC is negative CB, so I'm going to make that to go this. All right, so you think, oh, hang on, what's going on now? Well, those have disappeared, that's great. What happens if you get a vector and you dot it with itself? The square of the length, right? Okay, so this is just the length of that side squared. This is negative the length of that side squared. And because it's a square, this will be 0. Okay? So we would conclude, hence, AC really is yes. Thus, the diagonals intersect at right angles. That's it.